All right, so let's go ahead with the lecture. So last time we had talked quite a bit about computing matrix elements and inner products in the position and momentum representation. And so one more thing we want to do with that is to consider the commutator of position and momentum, for which we use the symbols capital X and capital P for the operators. The eigenvalues would be a lowercase x and a lowercase p. And so the way we're going to do this is we're going to consider any ket. Let's just give it a name psi. And we're going to consider the matrix element x, xp, the operator, psi. And according to what we learned last time, you can compute this as x times minus I h bar d by dx. That's the representation of the momentum operator in the position basis acting on the ket psi, or the wave function psi. Or just simplifying it a little bit, that's minus I h bar x d by dx of psi. Okay, and then we can also consider the same thing, but with the operator order reversed. So px. Okay, and so again, according to the rules that we figured out last time, this is minus I h bar d by dx acting on x times psi, where psi is again the wave function of the state or ket psi. Okay, and now we can use the product rule for derivatives to write this as minus I h bar x d by dx of psi, but an extra term occurs, minus I h bar times psi itself. Okay, the psi without the angle brackets, remember, is the wave function. It's a distinct thing. It's a function of x. It's distinct from the ket psi, which is just sort of an abstract representation of it on the Hilbert space. So having computed these things in different orders, we can now take their difference and ask for the matrix element of the commutator of x and p between the bra x and the ket psi. And so the first two terms cancel out, and we're just left with I h bar times the wave function, which we can also write as I h bar times x psi. Okay, and now comparing that expression and that expression, since they're supposed to be valid for any psi, we can conclude that the commutator of x and p is equal to I h bar. So this is a famous result. This is known as the canonical commutation relation for position and momentum. And depending on what book or source you're reading, this important thing can sometimes be introduced in a different way. So in some books, this is taken as the starting point, and then you sort of can work backwards to where we arrived, where we got into it with the representations. So there's different ways to approach it. I've just chosen here to introduce the representations of x and p first and derive the canonical commutation relation from them. But you should be aware that that was a choice. There are other ways of doing it. All right, so all of that was in one dimensions. So you have one-dimensional movement with a position and momentum, but you can straightforwardly generalize this to 3 dimensions. So in 3 dimensions, just to show you the notation that I'm going to use, we have an operator that I'm going to call capital R with a harpoon on it, which is defined to be x hat times x plus y hat times y plus z hat times z. And so this whole thing is an operator. Okay, and then there's a corresponding momentum operator, capital P, which is x hat p sub x plus y hat p sub y plus z hat p sub z, which is another operator. And within them, they each contain operators. So each of the components are operators. But the x hat, y hat, and z hat are constant vectors, not to be confused with vectors on the Hilbert space. These are vectors in space, ordinary space, not the Hilbert space. Okay, and so y is just like x, except it's in a different, it represents a motion in a different direction. And so now the canonical commutation relations you can get just from what we did for x. So in particular, commutator of x with px is the same as the commutator of y with py. That's not what I meant. Py is the same as the commutator of z and pz. Those are all each independently equal to I times h bar. And then every other commutator of all of these operators is 0. So for example, x commutator y and x commutator z and y commutator z, those are all 0. The same thing for the corresponding momenta. So px and py and px and pz. Those commutators and py and pz, those are all 0. And if you take the commutator of x with a different momentum, like the y momentum, or the commutator of y with the z momentum, those are also. So there's all these different combinations, and they're all 0. Okay, and now you can write down the eigenkets of position and momentum. And just as a reminder, these are not states in the Hilbert space technically. These are idealized eigenkets because they don't have finite norm, but they're defined by the operator R, the three-dimensional position operator, acting on the eigenket little r is equal to the eigenvalue, which is now a vector in space, r, times r back again. So here, little r is x hat x plus y hat y plus z hat z. It's not an operator. It's a numerical vector. And p acting on little p is similarly little p, the eigenvalue, times little p, the ket, where little p is p sub x, x hat, plus p sub y, y hat, plus p sub z, z hat, where for no good reason I wrote them in the different order. And then you can continue to steal the results that we derived in one dimension. So for example, the inner product of r with p is equal to phi sub p. It's a function of r, it's a wave function. And it's just the product of the 3 to 1 dimensional one. So there's a 1 over square root of 2 pi h bar, but now it gets cubed, times e to the I p dot r divided by h bar. That's just the product of the 3 exponentials. And then you can do, for example, r prime r, inner product. That's the 3-dimensional delta function of r minus r prime. And the definition of that is it's the product of 3 individual 1-dimensional delta functions. So it's delta x minus x prime, delta y minus y prime, delta z minus z prime. Okay, and similarly for momentum eigenkets, they are a 3-dimensional delta function of p minus p prime, which is just defined to be the product again of three one-dimensional delta functions.
Excuse me, could I ask a question about the idealized Ekets line?
Yes.
Are you setting up an eigenvalue equation there?
So
Where
yeah,
it's like,
this is an eigenvalue equation. These are eigenvalue equations. And then the solution to the eigenvalue equation you can write by finding the wave function. And so this is basically telling you the solution to the eigenvalue equation for P.
so I guess I'm confused at the vector symbols everywhere. I would have expected it to be a matrix times a vector is equal to a scalar times a vector. I'm seeing vectors times vectors on all sides, and also vectors of kets, or kets of vectors. It's confusing.
Right. So the confusion is that there are two different types of vectors here. There are the vectors in the Hilbert space. Those are being represented by the ket symbols and the bra symbols, the angle brackets. Then there's the vectors in three-dimensional space, which are a completely different kind of vector. And those are the symbols with the harpoons. So that's the challenge, is to keep those things straight in your mind. So everything that I've written here, when I mean a vector in the Hilbert space, I'm using ket notation. And when I mean a vector in real space, I'm using the harpoon notation. And so if you would think back to when we introduced all this ket and bra notation, you might have asked, why did we bother with that? And this is showing why we bothered, because we have two completely different kinds of vectors, and we need to keep them straight with notation. And so that's why kets and bras represent vectors in the Hilbert space, and harpoons and hats represent vectors in the real space.
Can you confirm if, I'm just trying to make sure I understand the difference between the two. Hilbert space is like X versus P, right?
Hilbert space is the space of states of the system. And so X and P can be labels for particular elements of that vector space. But the real, I'm trying to figure out how to say it, the vector space of spatial and momentum is represented by these, orthobasis elements are X hat, Y hat, and Z hat. Right? So those are the things that point you in real space directions. And then in the Hilbert space directions, we have orthobasis kets that are the whole thing. R is one orthobasis and P is another orthobasis.
So, I guess Hilbert space is a very abstract concept. And I might be asking you to repeat yourself, and I'm sorry for that, but what exactly, again, is represented in Hilbert space? Like,
so the Hilbert space vectors are telling you what's the state of the system.
okay.
And the ordinary vector space is telling you directions in 3 dimensions.
Okay.
So that's the distinction.
Okay. Thank you.
Okay, good. All right. So another way of defining the 3-dimensional delta function is the following. Oops, I'm using my laser rather than my ink. Okay. So you could define the 3-dimensional delta function by the following equation. That if you integrate over some volume in 3-dimensional space of the 3-dimensional delta function of, let's say, r minus r prime times some arbitrary function, f of r, the result is one of two things. It's either f of r prime That's if R prime is in the volume V. Or it's 0 otherwise. So if R prime not in the volume. And so what's this D3R? This is, one way we can write it is just dx times dy times dz, the product of the differentials in ordinary one-dimensional space. Or we could write it in spherical coordinates, where it takes the form r squared dr d cosine theta d phi. Okay, and if you do write things in spherical coordinates, then the three-dimensional delta function could also be written as delta of r minus r prime divided by r squared, delta of cosine theta minus cosine theta prime times delta of phi minus phi prime. So that's if you're choosing to use spherical coordinates to do your integration. Okay, and then finally, just to show how you represent things in three-dimensional space, I can make a little table here. Oops. I can make a little table here of position operator, which is a vector, momentum operator, which is a vector in 3 dimensions. And then there's an R basis, and there's a P basis. Okay, and R in the R basis is represented by the vector little r. You should think of that as a number that happens to be a vector also. P is represented by minus I h bar times the gradient. The R in the P basis is represented by positive I h bar gradient with respect to P. And P in the P basis, of course, is just represented by the vector P. So here, the gradient sub P is x hat, derivative with respect to P sub x, plus y hat, derivative with respect to P sub y, plus z hat, derivative with respect to P sub z. Okay, so we are going to eventually come back to three-dimensional problems. We won't be doing three-dimensional problems, I think, for a little while. But when we do, we will want to make use of these formulas. Okay, so it's finally time to return to something we had started and then took a detour, and that is the postulates of quantum mechanics. So earlier we did the first 2 postulates, and then we said, oh, let's take some time to learn the math. And now we're ready to come back and do this again. So let me restate the first 2 postulates. Postulate 1 says the state of a system. That could be a particle, a collection of particles, or maybe just the spin of a particle. In any case, it's represented by a ket, psi, in a Hilbert space. So notice that this is a postulate, so it's sort of circular. You could say, what is this Hilbert space? It's the thing that represents the state of a system. Okay, now the norm of the ket psi must be finite. That's why the position and momentum eigenstates are not technically members of the Hilbert space, they're idealized examples. So this must be finite, non-negative, but it's not otherwise physically significant. So you get to choose it. Many times it's convenient to choose it to have norm 1. But it's important to realize you don't have to do that. It's just very convenient in certain things that you're going to do. Okay, the second postulate has to do with observables, which are things that you can measure or talk about having measured. And observables correspond to Hermitian operators on the Hilbert space. So that means we proved that they have real eigenvectors. And if it's finite dimensional, they can also be chosen to be an orthobasis. But because we will sometimes, and in fact often, talk about infinite dimensional things, we add here that the eigenkets can be chosen as a complete orthobasis. So in the infinite dimensional case, you can find examples where something is a Hermitian operator, but it does not have a complete orthobasis. And in that case, it's not an observable. It's just a Hermitian operator. It's not something you can measure. Okay, so postulate 3 says, what can happen if you do a measurement? So the measurement of an observable, just to give it a name for the following, let's call the observable A. It always must give one of its eigenvalues as the result. There are no other things that can happen. So we'll call those eigenvalues alpha. So again, these are postulates. You're not allowed to argue with these. Well, I guess you can argue with them, but the answer to, if you say, why does it have to be an eigenvalue? The answer is just, that's the way it is. If you don't like it, invent your own theory, compare it with experiment, and see which one works out better. And of course, postulates of quantum mechanics have turned out to work very well over many, many experiments. Okay, postulate 4 says, if you do choose to measure A, or somebody else chooses to do it, so if A is measured, what's the probability of getting a particular result? Okay, and so we have lots of things that start with the letter P, unfortunately. So I'm going to call probability curly P. The probability of getting the result alpha is, according to this postulate, the sum over all rho sub alphas of alpha rho sub alpha psi squared. Okay, and so what are these things? These are the orthobasis elements that you were promised in postulate 2. And the rho sub alpha are degeneracy labels because there might have been more than one orthobasis element with the same eigenvalue alpha. Okay, now another way of writing this is just psi p alpha, notice it's not a curly p, psi. Okay, and all of this is where psi was the state just before the measurement. And this is assuming that you've already chosen the normalization so that it's 1. That's why it's convenient to make that, to make it normalized to 1 so that you can apply this postulate in a straightforward way. Okay, and P sub alpha is a sum over our degeneracy labels of alpha rho sub alpha, alpha rho sub alpha. So notice that's a sum of projection operators. Okay, now if you don't happen to have a degeneracy, then it's not a sum of projection operators, it's just a projection operator because there's only one state there. But it's the sum of projection operators for the orthobasis kets with eigenvalue alpha, however many of them there are. Okay, now the way we've written this assumes that alpha was not continuous, that it was some discrete set of numbers like 1, 2, 3 or something like that. And then you could say, what happens if it is continuous, like position or momentum? If A has continuous eigenvalues, alpha, then you talk about the density of probability. That is the probability of getting a result between two different values. Probability of measuring a result between alpha and alpha plus d alpha is given by d alpha times curly p of alpha equals d alpha sum over rho alpha, alpha rho alpha psi. So you compute this inner product and you square it and then you sum over the rows of alphas. Okay, note that you do the sum after you take the square. The complex square. So a common mistake is to do the sum first and then take the complex square. So that you should not do. You should take the square first and then sum, and it makes a difference. Okay, so postulate 5 says what happens after you make a measurement. So measuring A is said to collapse the state. And so what does that mean? That means I start with a state psi. I do this process of measuring A. And let's say I got the result alpha. Then the state after the measurement is this projection operator or sum of projection operators, P alpha, acting on psi. Okay, so this is the state just before. This is the state just after the measurement. And notice that it's not normalized to unit norm. But you can always take it and make it have unit norm by dividing by 1 over the square root of its norm. Okay, now this thing will be a linear combination. So equals linear combination of kets with eigenvalue alpha. Okay, so it's not just any linear combination of kets though. There's a very specific recipe that gives you a answer, which is you construct the operator P sub alpha as a sum of projection operators. You act on the state psi that you were given just before the measurement, and that tells you what the result is. You may have to divide by 1 over the square root of its norm to get a unit norm, but in any case, that's the result. Okay, and then finally, the last postulate is postulate 6, which tells you the time dependence of a state. So now I'm going to label it by time, t. And this is in the absence of a measurement. So postulate 5 is telling you what happens if you do make a measurement. This is saying what happens if some period of time goes by and you're not making a measurement during that time. Then the state evolves according to IH bar, time derivative of the ket psi of t is equal to h, which is going to be the Hamiltonian, times psi of t. So this is known as the Schrodinger equation. That's just the name for it. H here is the Hamiltonian, which is an operator for the total energy. Okay, and it's not only Hermitian, it's an observable itself. So it plays two roles. It's something you can measure, and it's something that tells you the differential equation by which the state evolves, this differential equation right here. Okay. So just for example, for a single particle without spin, then the Hamiltonian is going to be a kinetic energy operator, p squared over twice the mass, plus a potential energy, which we're typically going to call v of x. So capital P here is the momentum. As we've done before, capital X is the position. And the potential that our particle is reacting to is capital V of x. So it's an operator that's a function of an operator. Okay, so some weird things can happen if you have functions of operators. Some quantum mechanical observables have no classical counterpart, so have no classical version. And a good example of that we'll talk about much more later is spin. But even if it does have a classical version, it can be somewhat ambiguous. So just for example, given a classical function of position and momentum, A of x and p is some function of position and momentum, the quantum operator let's call it capital A of x and p is ambiguous in general. Sometimes it may not be ambiguous. Okay, so just as an example, let's say my classical observable is just the product of position and momentum. So one thing you could try is you could try to define capital A equals the product of the corresponding operators. The problem with that is you can check that this is not Hermitian. And if it's not Hermitian, that means it's not eligible to be an observable. Okay, so you can define the operator, but it's not something you can measure. On the other hand, you can try 1/2 x times p plus p times x, sort of the average of the different possible ways you could order it, and that it turns out it is Hermitian. So that could be an observable, and so it's something you could measure, even though classically those two things look like the same thing. All right, so now let's define some other concepts. First, there's the expectation value. Notice this is not anymore one of the postulates. This is stuff we're deriving from the postulates. The expectation value is the answer to the question, what is the average value obtained by measuring A, an observable, in a state psi? So to answer this, you need both a state and you need an observable. And the way you would answer this experimentally in the real world is you'd prepare many states in the same exact, or many systems in the exact identical state and do it many times and take the average. So given many identical copies of a system. You measure it many times and then you take the average. So it's a very statistical thing. And so let's compute this thing. First of all, we denote it as just A between angle brackets. It's the sum over all possible things you could measure as a result, alpha, of the thing you got, alpha, times the probability that you got it, P of alpha, curly P of alpha. And now postulate 4 tells us what that is. It's sum over alpha, sum over the degeneracy of alpha, of psi alpha rho of alpha, alpha rho of alpha, psi. That's postulate 4 in action. Okay, and now we can write, oops, I forgot a very important thing. This would just be 1 if I didn't put in my alpha here, which is very important. And now I can write this as sum over alpha, sum over rho sub alpha of psi A, the operator, alpha rho sub alpha, alpha rho sub alpha psi. So what have I done there? I've used the fact that these are eigenkets. The alpha rho alpha are eigenkets of A. Okay, and so I changed my alpha into an A. Okay, and now I can use completeness because this is psi A psi by completeness. And that's why it was important that the eigenkets of A really were a complete orthobasis and not just maybe some subset of an orthobasis. Okay, and so note, we have assumed in doing this that psi was normalized to 1. But again, that's optional. What if it wasn't normalized to 1? Otherwise, the expectation value of A would be defined to be psi A psi, that matrix element, divided by the norm squared. Okay. All right. Then there's the concept of the uncertainty, another statistical thing that you can talk about for states and operators. So this is also a property of the observable A and the state psi that you find yourself in or that you're given. Okay, and here's its definition. Actually, it's nicer to find the square of the uncertainty. Delta A squared is the square of the uncertainty, is equal to the expectation value of a particular operator, which happens to be A minus the expectation value of A squared. Okay, so to do this, you compute the expectation value of A, then you subtract it from A, then you square it, and then you take the expectation value of the whole thing. That's just the definition. And now we can write this in a more simplified way as psi A minus psi A psi all squared. But that's a kind of a clunky thing to compute. So we're going to expand this to get a nicer form for computing things. Okay, and when you do, you find out this is the expectation value of A squared minus the square of the expectation value of A. And so that's a nicer version of the definition. This is the uncertainty squared. Okay, and that's this second version is what in practice you're usually going to just plug right into that to get your uncertainty. Okay, and again, we've assumed that we normalize this thing to 1. If not, it's okay. You just divide by, you divide your answer by psi psi, if it's not 1. All right, so let's do an example that will be somewhat similar to homework 1 problem. I'm going to define two observables, A and B, and A is going to be represented by the matrix 1/2 times the matrix 1, 0, 0, minus 1. And B is going to be represented by an operator 1/2, 0, I, minus I, 0. Okay, and these are both Hermitian, but they do not commute. They're not compatible operators, which means they commute. But that's okay. Nobody ever promised you that operators would always commute, and a lot of times they won't. Okay, and so the eigenkets of A are going to be an orthobasis because A is an observable. And the orthobasis can be labeled by the eigenvalues of A. So I'm going to call them the ket 1/2, which is represented by the vector 1, 0. This has eigenvalue 1/2 for A. And the ket minus 1/2, which is going to be represented by the vector 0, 1, which has eigenvalue minus 1/2. Okay, so now we can ask about things like, what's the expectation value of B in the state minus 1/2? So minus 1/2 is an eigenstate of A with eigenvalue minus 1/2, and we're asking what's the expectation value of B in that state. Okay, so to do that, we compute minus 1/2 B minus 1/2. That's from the definition of expectation value, which is going to be 0, 1 complex conjugate, even though 1 is real, and so the complex conjugate doesn't actually do anything here. It's a good habit to get into, to just put it there anyway, to remind yourself. And then the matrix representation of B is 1/2, 0, I, minus I, 0. And then the matrix representation of the ket minus 1/2 is 0, 1. Okay, which is 1/2, 0, 1, because the complex conjugate didn't do anything, times I, 0, which just happens to be 0. Okay, so that's saying the expectation value of B in the state where A has eigenvalue minus 1/2 is 0. All right, let's do an uncertainty. So the uncertainty of B in the state, again, we'll use minus 1/2 just as an example. So we're computing the uncertainty of B in a state where A is certain to be minus 1/2. Okay, and to do that, we need, according to this, this formula up here, except we're going to be using A equals B in that formula. We need the expectation value of B squared. So let's compute that. Okay, that's equal to 0, 1. The square of B looks like this. And then we have 0, 1 again. The 0, 1s are representing the state minus 1/2 in this matrix representation. This square here is equal to 1/4 times, it turns out, oops, the identity operator. Okay, and when you multiply that all out, you get 1/4. So the uncertainty in B squared is equal to minus 1/2 B squared minus 1/2 minus the square of minus 1/2 B minus 1/2. Okay, and we just worked out that this is 1/4. And we also worked out that the expectation value of B in this example happened to be 0. It won't always be. Okay, and so we get 1/4, and therefore, by advanced methods, the uncertainty in B is 1/2. Okay. Another thing that you can ask, according to the postulates, is what are the possible outcomes of measuring B? Okay, and so for that, the postulates tell us what we need are the eigenvalues of B, which turn out to be, one of them is plus 1/2, and the corresponding eigenvector is 1 over the square root of 2, 1i. The other possible eigenvalue is beta is minus 1/2, and it turns out the corresponding eigenket is 1 over square root of 2, 1 minus I. Okay, but all we need really is the eigenvalues here. It's 1/2 and minus 1/2. The reason I wrote down the eigenkets also is because of the next thing we're going to do, the next question we're going to ask, which is, let's say we're in the state minus 1/2, which is an eigenket of A with eigenvalue minus 1/2. What's the probability of getting plus 1/2 for B? Notice plus 1/2 is one of the options because it's an eigenvalue of B. If I asked you what was the probability of getting the answer 0, the answer would be 0. There's no way that you can measure B and get the answer 0 because it is not one of the eigenvalues. Those are the allowed results. Okay, so the probability of getting 1/2 for B is the curly B of beta equals 1/2, which according to the postulates are, we're supposed to compute this inner product, minus 1/2 with beta equals 1/2. So we're supposed to take the square, oops, I don't want to use angle brackets anymore. We're supposed to take the square of 0, 1 star. That's the representation of the state minus 1/2. And then the representation of the state beta equals plus 1/2 is this thing. Okay, so here I'm going to write 1 over square root of 2, 1i. And then when I'm done taking that inner product, I'm going to square the whole thing. So this is going to equal I over square root of 2 squared, which is equal to 1/2. Okay, so as a reality check, notice that this thing is a reasonable probability. It's got to be real. it's got to be positive, and it's got to be between 0 and 1. If it doesn't satisfy those conditions, just in general for any probability problem, then it means you made a mistake somewhere. And there's no contradiction in the postulates of quantum mechanics. They're known to be consistent. And so it must be just an arithmetic mistake that you made. Okay. Now, if you're in the state -1/2 and the that's an eigenket of A, and you did get the probability 1/2 for B, then the state after the measurement is going to be the following. It's going to be the projector onto beta equals 1/2. That's a specific operator acting on the ket -1/2. This is the state after the measurement. In this example, there's no degeneracy in the eigenvalues for B. So this thing right here is the operator beta equals 1/2 ket, beta equals 1/2 Ra. And so the state after the measurement let me write it this time in ket notation, is going to be 1/√2 times, now I'm writing things in the A representation and the eigenvalues of A. So this is 1/2, I'm going up here to this. So 1/2 plus I times -1/2. Then I write it again, but in the Bra language. So this is 1/2 minus I -1/2. And then all acting on the ket -1/2. So all the labels here are A eigenvalue labels. Okay, so I won't do the final arithmetic, which is to reduce this by taking these inner products. That's the sort of thing you'll be doing for homework, though. Okay, so sorry I went over time, but I did want to go over one example that would be similar to that homework 1 problem before you actually have to turn it in, which is going to be on Wednesday. Okay, so are there any questions? Maybe I should turn off the recording.